This is CPE 133. This is an introduction to Verilog modeling, and it roughly covers chapter 4 in the free range Verilog Foundation modeling text. This is part 1 or part A of 2 videos. So there are essentially 2 approaches to modeling digital circuits using Verilog. Essentially it's the high level and low level. And now this chapter, we're just introduction, we're going to use the low level. Now this is typically what I refer to as data flow modeling, and the high level is referred to as behavioral modeling, which we'll get to later. So data flow modeling, the notion of data flow is primarily a VHDL term. It's not super well defined, but I typically use it to mean like a low-level design, which typically means a gate-level design. So, you know, the issue with the gate-level designs, you gotta know exactly what you're doing on the logic level. Now, with behavioral modeling, that's not the case, and we'll get to that later. Essentially, there's actually 2 approaches to using this gate-level modeling in Verilog. One of them is just really confusing, and you don't need to know it. Where the approach we're taking in here is in my mind much easier. So this data flow approach that we are talking about, technically speaking, is actually a form of behavioral modeling, but I don't really call it that because it is low-level modeling. It is gate-level modeling. I just prefer to call it a different name, because as you'll see, behavioral modeling is a distinctively different thing. So Verilog models in general divided into 3 parts. It's the external interface, internal circuitry, and internal interface. So the external interface is how the outside world sees the circuits. Namely, it's the inputs and outputs to the module you're designing. So the internal circuitry is the notion of all the modules and gates inside the circuit you're designing. Typically, you know, this is digital design. It is hierarchical. We will be designing modules. Now, the notion here is that a gate is a type of a module or a box. So it is, technically speaking, some form of hierarchical modeling. So the internal interface is simply a method of providing signals to connect your internal boxes, and we'll see that in the examples coming up. So this is the example we're going to use here. It's just a simple, and/or circuit, and then the issue here is model it using Verilog, but use only one statement. Now, so the issue here is even with this simple circuit, there's just like literally an infinite number of ways to model it. We are going to use one way, then we're going to do it again using another way, but you'll see pretty quickly that Verilog is pretty flexible, and there's lots of ways to do things in it. But anyway, we want to use this with only one statement, and you'll see what that means as we go along here. So once again, this is what we're going to do: generate the interface, and then move to the other step. So the first step is to generate the interface. And so here it is, and nothing fancy about it. It is somewhat some special syntax. You can see from the circuit that A, B, and C are in fact inputs, and so we are going to declare them as inputs with the input keyword in Verilog. You'll see there. F is the output. We're going to declare that with the output keyword. Pretty exciting. So this is the interface, but it's actually the entire module. What we need to do is fill in some other stuff. Now this is actually one of 2 ways to define this interface. The other way looks more like C programming. I actually prefer this way. Notice that there is one input listed per line. I actually could put them all in one line, but it's always better to put them separately. You'll see later that I do kind of clump them together to save space. And I think that's it on this. So that's the interface. That's what the outside world sees, and we're going to add stuff on the inside here, and let's see how it goes. Okay, so this is how we're going to assign the internal circuitry here, and what we're going to use here is an assign statement. More on that later. So essentially assign is a keyword, and we are going to assign that output F. Now that output F is going to be A ANDed with an inversion of B, and you can see that hopefully that here is the AND operator. It's actually it's 1 ampersand, which indicates a bitwise AND operator. Here is the tilde, which is the inversion operator, and so this implements A and not B, and so this implements A and not B, which is this gate up here. So tilde A, well, not A and C is the other gate here, but in between these is this vertical bar, which is the bitwise OR operator. So this line here represents the internal circuitry of this module. And once again, the sign statement is something special. We'll get to that in a second. Oh, lastly here, I forgot to say, this is actually pretty important. I know Verilog has operator precedence on these logic operators, but honestly, I don't know what they are. And I don't know what they are because I never use them. And so the issue is I always use the parentheses. That way I don't have to know the precedence the operator precedence, and also it just makes it easier for humans to read. The message here is don't rely on operator precedence. Always use parentheses when you can. So this one statement is a special type of statement. It's called a continuous assignment statement, which we'll get to next. But we were able to implement all the internal circuitry on one line in this one. So there's only one line that represents the internal circuitry. So let's take a look at that line a little bit closer here. And this is, like I said, a continuous assignment statement. And so if you look on the right side of the equal sign, there's 3 variables there. So what's going to happen is this assign statement is going to be that the F output is going to be reevaluated anytime there's a change in any of the signals on the right side of the equal sign. Okay, so that's the continuousness of it. Something on a variable on the right side changes, it's going to cause a reevaluation of the variable on the left side. Continuous assignment, one of the mainstays of Verilog is the continuous nature of things. And so anyway, so we'll get to that later. There's also the notion of behavior modeling, which also has the notion of a continuous assignment, but it's a little bit different. So we'll talk about that when we get there. Okay, so this is another example, same example, but it says use one continuous assignment statement for each gate in the circuit, and assume each gate is, assume an inverter is not a gate. So essentially that's going to allow us to use that tilde operator again. And so the notion here is generate the interface. It's the same as before. A, B, and C are inputs, F is output. And then all I have to do on this thing, which is create 3 assignment statements here, and one's for each gate there. Now, nothing too fancy about this, but it's a little bit confusing because it's a notion of how exactly do those X and Y signals connect to the OR gate. And so this is kind of an implicit way to do it, and it's not a good way to do it. You shouldn't do it this way, and here's the better way. So this is the better approach here, and that we're using internal interface. So the whole point of this example is that it uses an internal interface, which provides a way to connect those gates. Now the internal interface that we're going to use here are wires. These wires, I like calling them intermediate signals. Essentially, they just provide, a placeholder for the output of those gates before they're ORed together. Now this solution is functionally equivalent to the previous solution, but it is better because I've explicitly declared the internal interface, which is those 2 wires X and Y. I didn't have to, but it's just way better to do it that way. So the issue is within this example is it declared those wires explicitly, The problem being that it only will explicitly declare wires that are 1 bit wide. So if you have wires that are multi-bit wide, it's not going to work. So it's always better to make your internal interface signals explicit rather than implicit. Okay, and so the issue here, wires, they're actually referred to as nets in Verilog. I know I often use the word variable, but variable is actually something different. Typically what we use it for is to connect inputs and outputs in the circuit. So typically speaking, that I like referring to them as intermediate signals. It's connecting modules in your circuit. These are analogous to wires in a physical circuit, and more importantly related to that is because there are wires, you don't have a wire floating. Something needs to drive that wire. These wires do not have the ability to store data, and you'll see later that technically speaking we will need signals that must store data, but we're not there yet. So once again, the unspecified input and output types in the external interface actually default to wire types. Essentially, you don't need to write wires on those, and we typically don't, but sometimes you actually do. And as you saw in this previous example we did, the unspecified intermediate signals default to a 1-bit wire type. But once again, you do not rely on those to work. You should always explicitly define your intermediate signals. So this is an example showing that the inputs and outputs are actually wires. When I say input and I don't say what it is, it's going to default to a wire type. And that typically, like I said, typically we don't write wires in the interface, but typically we do write wires in the internal interface, just not the external interface. So that's it for this lecture. There's a little bit more on part B, and we'll get to that next.